So let's move to the second problem. I have a cart. Second problem, I have a cart. This one has a mass A. Initially at rest, I have a bar. There is a mass. And I apply the velocity v0 in this direction to this bar. Okay? And then what is going to happen? This cart will move and the bar will go up. And the problem asked us to get VV at maximum elevation. And also it wants us to estimate this height. Okay? Then let's attempt to solve first problem. And what kind of tool we would like to invite? Star, moon, sun. Moon? Moon? Okay? Moon? No response. Moon? Moon? Star? Sun? Moon? Star? Sun. Why? Because it involves maximum elevation, that will introduce the potential energy change. Okay? I mean, inviting sun for solving second problem is rational. I can accept it. But what about first problem? First problem asks us to get maximum velocity at maximum elevation. And it all involves velocity. Maybe we just start to use the second, let's invite sun. Okay. Then the text said frictionless. We are very happy about that. But according to the second quiz, often you will be asked to include the friction, right? But this is a simple case, therefore assume there is no friction. Then the energy is conserved because no friction. Therefore, at state 1, the energy is 1/2 mb v0 square. At state 2 is 1/2 mb vv square plus mb gh. What is this vv? What do you mean by this? Huh? Okay, that's good. So he said VV is the velocity in this direction. I think there should be MA VA too, because this is moving too. Yeah? All right. Then maybe I can say that VV is equal to actually VA plus VB observed with respect to A. That is always true, right? Then let me ask you, what is this in this case? Huh? 0. Why? Why? Okay, let's see the simplest case. If it moves maximum over here, the velocity is 0, right? Over here, with respect to that point. That is obvious for this simple pendulum case. Okay, now that problem is this pendulum is moving. So simply the velocity over here is the velocity of this one plus the relative velocity of that one. That relative velocity is, as we learned before, should be 0 at maximum velocity. Okay? So that problem teaches us very important important techniques. When you get a complicated, rather difficult problem, you divide that difficult problem with what you know and what you do not know. Right? So this is what you do. So that is 0. Therefore, this is okay, and that is okay. Then immediately we can find that VV equal to VA over here. So we have VA, this is unknown. So we have one equation and 2 unknowns if I only apply the energy principle. And looking at this dynamics in terms of momentum, we found that momentum, linear momentum, is also conserved because there is no friction force in x direction. Right? So in x direction, we have in initial, we have linear momentum, and that has to be ma VA plus mb VA. That is ma plus mb VA. Therefore, from this equation, we can calculate VA. And then using the first equation, we can calculate maximum elevation because we have 2 equations and 2 unknowns. Let's examine whether or not this solution is sensible by looking at extreme case. Okay. If V0 is 0, then VA is 0. That's trivial case. Okay. If MB is very, very small compared with A, like I am putting small particle on a big truck and then I move it, then nothing will happen. That is also trivial case. If MB is very large compared with MA, then this is VA is equal to V0. That means I have a small mass and I have a big mass. I have a big linear momentum. It will move as if one particle. That makes sense. So this formula result makes sense. And what about the height over here? Okay. Height has to be equal to MB G, and then 1/2 MB V0 square minus 1/2 MB VV square, and minus 1/2 MA VA, that is the same as VV, so that is VV square. And I have to plug this value over here. Right? And first, if MB is very small, then the height should be very, very large. That makes sense. Is it? Strange. Oh. Second, if V0 is very high, then the height should be very high. And that is proportional to the scale of the velocity V0. And then the other one is also related. And I want you to look at some detail. Okay, now let me summarize what we learned today. We learned this. We learned this. And we use some example so that you are able to apply this concept for two mass case. Okay, and I hope you can apply those two methods. Any question?